Hello, Assalamualaikum. My name is Muhammad Mazarif Haikal, metric number 078584. So today I would like to explain about what is 8 puzzle and what's the problem explanation for this case study. So first we go for environment setup. For the grid structure, the puzzle is played on 3x3 grid, and the component is consists of 8 number tie, like 1 to 10, and have one blank space. The objective is goal to transform the puzzle from the initial state, scramble initial state, to the specific order goal state. Okay, thank you. For the second one is we go to movement and constraint. So the rule of sliding, you cannot pick up or skip tie, or tie can only slide if the adjustment to the black space. The AI perspective, eventually the AI solve the puzzle by the moving blank around the grid. Okay, like the picture we're gonna see next in the next slide. In valid action, there are 4 possible move for the blank space, which is up, down, left, and right. Boundary constraint, a move is only valid if the blank remain within 3x3 grid boundaries. For the second one is we go to movement and constraint. So the rule of sliding, you cannot pick up or skip tie, or tie can only slide if the adjustment to the black space. The AI perspective, eventually the AI solve the puzzle by the moving blank around the grid. Okay, like the picture we're gonna see next in the next slide. In valid action, there are 4 possible move for the blank space, which is up, down, left, and right. Boundary constraint, a move is only valid if the blank remain within 3x3 grid boundaries. And last but not least, we're gonna go at path cost. So we have only 2. The uniform cost, path cost is 1, is assigned to every single move, and optimization, the objective of the AI is to find the path with the lowest total cost, meaning the fewest step to reach goal. Thank you so much. I would like to pass to the next presenter. Thank you so much.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Akmal bin Rahman. My metric number 706380. So today I will walking you through the solution process for the 8 puzzle problem. A classic example is in artificial intelligence and search algorithm. Let's start with the initial state shown here. The puzzle consists of 8 number tiles and 1 blank space. Our goal is to rearrange this tile from the initial configuration into the full state, where the number are ordered from 1 to 8, with the blank space at the bottom right corner. To solve this puzzle, we can move the blank tile in 4 directions: up, down, left, or right. Each move change the arrangement of tile and bring us closer to the goal. Below the main state, you can see the search tree. Each box represents a possible configuration. After performing one of the action, the arrows show how the puzzle evolves step by step. At the top left, you will notice the first cost is 16. This means it took 16 moves to reach the goal state from the initial configuration. A measure of how efficiently the algorithm found the solution. As we follow the arrow, the brain tile moves strategically through different positions. Each move is chosen to minimize the distance to the goal, demonstrating how search algorithm like A-star or uniform cost search explore possible states. That's all from me. I will move to the next slide. Let's continue for this slide. Here is a simple implementation of the brute first search algorithm in Python. We start by defining the function DFS that the queue keep track of state to explore, and the visited set prevent revisiting nodes. Inside the loop, we pop the first element from the queue, thus our current state at path. If the state match the goal, we return the first. Otherwise, we explore all neighboring states, add unvisited ones to the queue, and continue until the goal is formed. If no path exists, the function return none. This approach ensures we find the shortest path in unweighted graph. This could show a tips limited version of the tip first search algorithm. We start with the function DFS limited, which takes a starting state and the tip limit. The state is used to keep track of state paths at their tip level. Inside the loop, we pop the top element, that's our current state. If the state match the goal, we return to the path. If the tip exceeds the limit or state or is already visited, we skip it. Otherwise, we mark as a visitor and push its neighbor onto the state with the implicit tip. This method helps prevent inverted loops and control how deep the search goes. This could demonstrate the greedy best first search algorithm. We start with the function greedy start, where priority queue store the base on their heuristic value. The algorithm always pick the state that look closer to the goals according to heuristic function. If the current state matches the goal, we return to the past visited state, are skipped to avoid repetition, and never are added to the queue with their heuristic value. This method is fast but not always optimal. It focuses on what seems best the moment rather than the overall shortest path. That's all from me. I will pass to the next presenter. Thank you. This could demonstrate the A-star search algorithm, one of the most efficient path-finding methods. We start by defining the function A-star start, a priority queue store state along with their heuristic value. The algorithm plots the state with the lowest estimate cost, check if the goals, and return the path is found. Visited states are skipped to avoid repetition. For each neighbor, we calculate the cost A with cost G to HN, combining the path length and heuristic, and push it back into the queue. This approach ensures we find the shortest and most optimal path using the both actual distance and estimate cost.
This section discusses the heuristic design used for the 8 puzzle problems. Heuristics are important in an informative search algorithm because they estimate how close the current state to the goal state. In this project, 2 heuristic functions are considered, which are the misplaced fields and Manhattan distance. These heuristics help to improve the efficiency of the search process by guiding the algorithms toward the better path. Okay, so the first heuristic is misplaced tiles, which count the number of tiles are not in the correct position. The smaller the value, the closer the puzzle is to the goal state. Although this heuristic is simple and easy to calculate, it is less accurate. And the second heuristic is Manhattan distance. This heuristic calculates the total horizontal and vertical distance each tile needs to move to reach its correct position. Because it gives a more accurate estimations, it is more effective in guiding the search process. The Manhattan distance is considered more suitable for the 8 puzzle problem for several reasons. First, it is admissible, meaning it's never overestimate the actual cost to reach the goal state. This guarantees that A can find the optimal solution. Second, it is consistent because the heuristic difference between state is always less than or equal to the actually moved cost. So this helps A to perform more efficiently. So lastly, the Manhattan distance is more effective than misplaced tiles because it provides a more accurate estimate of the remaining move and reduce the number of explored states. So the Manhattan distance heuristic significantly improve the performance of A search algorithm. Compared to BFS, which explores state without guidance, A with Manhattan distance expands fewer nodes. This reduces both execution times and memory use. So the heuristic also help prioritize states that are closer to the goal state, making the solution process more faster and more efficient, especially for highly scrambled puzzles.
Hi, Assalamualaikum. My name is Nurul Shahida binti Muhammad Shafri. My matrix number is 078058. In this project, several optimization techniques were used to improve efficiency of solving the 8 puzzle problem. First, a visited set was implemented to prevent the algorithms from revisiting the same state repeatedly. Next, the Manhattan distance heuristic was used because it provides a more accurate estimate of the distance of the goal state. A-star search also used a priority queue to select the most promising node first. In addition, unnecessary move were prone to reduce redundant exploration. Finally, suitable data structures such as queues, state, stacks, priority queues, and hash set were used to improve the overall performance of the algorithm. Based on the comparison results, BFS guaranteed the optimal solution because it explores not level by level, but it requires high memory usage and longer execution time. DFS uses less memory because it explores one branch at a time, but it does not guarantee the shortest solution. Greedy best first search is faster because it uses the Manhattan distance heuristic, although the solution is not always optimal. Among all algorithms, A-star search showed the best overall performance because it balanced speed, efficiency, and optimality.